Hi, my name's Dennis. I'm an XRPL core developer at XRPL Labs, and today we're going to be talking about the NodeStore. So first, we're going to talk about the NodeStore overview and the purpose in the XRPL Ledger. We're going to talk about node object structure and data types, the caching layer and performance optimization, rotating database architecture, data encoding and storage formats, application architecture integration, and performance and scalability considerations. So first, what is the NodeStore? It is the primary data source interface for the XRP Ledger entries. It allows for persistent database abstraction layer, and it's the bridge between application logic and storage backends. Its core purpose is to store all ledger entries as node objects, provide a consistent interface across different storage backends, and ensure data persistence between application launches. The NodeStore overview, its primary functions are persistence management, so ensure that data survives across application restarts. It has an abstraction layer which hides backend complexities and allows for bolt-on backends. Memory management, which coordinates between cache and persistent storage and maintains consistency across storage operations for data integrity. The node object structure includes the type, which is an enumeration defining content type, the hash, which is a 256-bit unique identifier, and the data, which is a variable length serialized payload. The different node object types are the ledger headers, which contain ledger metadata, sequence numbers, timestamps, parent ledger references, and consensus information. Another node object type are signed transactions, so complete transaction data, digital signatures, transaction metadata, and fee and sequence information. We have account state nodes, which are account balance information, so trust lines and settings, object ownership data, and state tree structure. And finally, we have the transaction tree nodes, which is the transaction organizational data, Merkle tree structure, transaction indexing, and historical references. Next, we have the caching layer strategy. We have multiple different caching hierarchies. So L1 cache, which is recently accessed objects in memory, the L2 cache, which is frequently accessed objects, and then persistent storage, which is a full data set on the disk. The cache management strategy is an LRU eviction, so the least recently used objects are removed first. We have size-based limits to prevent memory exhaustion, type-aware caching, which allows for different policies for different object types, and predictive loading, which anticipates the future access patterns. The next thing is rotating the database architecture. So we have multiple database instances in rotation for seamless switching between active databases and continuous availability during maintenance. The strategy is that we have a primary database which handles all current operations, a secondary database which is synchronized, backup, ready for promotion. We have a rotation process which is controlled switchover with zero downtime. And we have a maintenance window for safe updates on active databases. The benefits of this are zero downtime maintenance, improved fault tolerance, performance optimization opportunities, simplified backup procedures. Next, we'll talk about data encoding in the storage format. The encoding strategy is a binary serialization, which is a compact, efficient format. Type prefixing, so self-describing data structure. Hash-based integrity for built-in corruption detection. And network optimization, which allows for minimal overhead for transmission of data. The storage format benefits are space efficiency, fast deserialization, cross-platform compatibility, and version tolerance, which can handle format evolution. Next, we'll talk about the application architecture integration. The integration points are the consensus engine, which stores validated ledger data, transaction processing, which persists transaction results, the network layer, which provides data for peer synchronization, and API services, which support client queries for operations. For performance and scalability, some of our performance factors are the cache hit ratio, which is a percentage of requests served from memory, data latency, so the time to retrieve the persistent storage, serialization overhead, which is the cost of encoding and decoding the data, and the memory usage, which is the balance between cache size and available RAM. For scalability strategies, we have horizontal partitioning, so distributing data across multiple backends, read replication, so scaling read operations independently, cache warming, which means preloading frequently accessed data, and batch operations to optimize bulk data operations. The NodeStore is a foundational component for any system that needs to persistently, efficiently, and securely manage discrete units of data. By organizing data in a uniquely identifiable node objects, abstracting the storage details, and focusing on integrity and performance, the NodeStore enables complex systems such as ledgers, databases, or distributed records. The NodeStore enables complex systems such as ledgers, databases, or distributed records to function reliably at scale. Thank you.